Hi, I'm Zor. Welcome to Zor Education. I would like to talk a little bit more about linear inequalities. However, a very simple linear inequality approach was actually explained in the previous lecture. Here I would like to expand this a little bit into linear inequalities which are related to inequalities with absolute values of linear functions. Just as an example what I mean, you have an inequality, for instance, like this. Absolute value of one linear function minus, in this case, plus whatever, of another linear function is less than 0. So it's not exactly linear inequality. However, what's important is it can be analyzed and basically solved as a result of this using an approach which was explained in the previous lecture of linear inequalities, but you have to do something before using these techniques for playing linear inequalities, as I was saying. So what are these techniques? Well, let's think about absolute value. What is an absolute value of the number? Well, the absolute value of the number is, by definition, so I'm not really asking anybody's proof or anything like that, it's equal to z for z greater or equal to 0. So for all non-negative numbers z, and I'm talking about real numbers, of course. So for all real numbers which are greater or equal than 0, absolute value of z is exactly the same as z. The absolute value of 2 is 2, absolute value of 25 is 25, absolute value of 0 is 0. So I don't have to do anything with the number z if it's non-negative to obtain the absolute value of z. I just should take it as it is. Now, what if z is negative? Well, if z is minus 2, then we know that its absolute value is 2, right? How can I get 2 from minus 2? Well, I have to negate it, right? So if I negate z, which is negative by itself, then I will get the corresponding positive, right? Minus of minus 2 is 2. Minus of minus 25 is 25. So if I negate my negative number, I will get its absolute value. So this is the definition. I was just trying to explain it. It's not a proof, it's just an explanation why this definition is important. So if I want to approach my absolute value of something, I have to first of all figure out where this something is equal to 0, and to the right of this value, I can replace my absolute value with the number itself. To the left of this value, I should really replace it with minus this particular number. Okay, now if I have a combination of certain number of absolute values of something, the best approach is to have the x-axis and mark where exactly each one of those is equal to 0. Well, obviously this one is equal to 0 at minus 2, and this one, x minus 1, is equal to 0 at 1. Now, these 2 points divide my x-axis, which means all the real numbers, into 1, 2, 3 intervals. So this is one interval, this is another, and this is the third. And on each of these intervals, I can consider this particular inequality, and on each of these intervals, I can basically convert it into a linear inequality and solve it. And let's do just this. So we have 3 different cases. This is area A, this is area B, and this is area C. So let's consider area A. Now A is x less than minus 2, right? Everything to the left of minus 2. What do I have? I will free some space for... Okay, so what do I have? Now, x plus 2 to the left of this, which means this thing is negative, x plus 2. So to get the absolute value, I should reverse the sign. So it would be minus, and now I have a regular parenthesis, x plus 2. Minus, what about x minus 2? Well, if I am here in this area, it's still to the left of this one. Now this point is where the expression x minus 1 is equal to 0, and everything on the left, which means this as well, would necessitate to replace absolute value with a negation of this. So it would be minus x minus 1. And that should be less than 0. Well, this is a linear inequality. So I replace my x plus 2 with minus absolute value of x plus 2 with minus x plus 2. I replace my absolute value of x minus 1 with minus x minus 1. And what do I have now? Well, let's open parentheses. Minus x minus 2 plus x minus 1 less than 0. Minus 3 less than 0. Always. Which means that if x is less than minus 2, I don't have any new restrictions on x, which means all x's which are less than minus 2 fit my equation. My inequality. Which means it's a solution. It's one of the solutions. All right. Next. So this is a solution. It's one of the solutions. Next, let's consider that minus 2 is less or equal to x less than 1. Notice that I'm using less than equal here, not just less than, just in order to include minus 2. By the way, in the definition of the absolute value, again, z is equal to z if z is greater than equal to 0, and minus z if z is less than 0. Actually, it doesn't really matter whether we use this or this for z equal to 0, because it will be 0 anyway, right? Plus 0 or minus 0. So that's why we have to include the points minus 2 and 1 into one of the areas. So in this particular case, I always include the point to the area which is to the right of it. So in this case, to the area B. That's where minus 2 will be included. And in this particular case, what I can say is that this particular absolute value should really be like this, because it's positive, right? If x is greater or equal than minus 2, I can replace absolute value of x plus 2 with just x plus 2, because it will be 0 or positive. Now, up to this point, which is where the B area is ending, this expression will still be negative, which means I should really replace it with its negation. So what's the result of this? X plus 2 plus x minus 1 less than 0, 2x plus 1 less than 0, x less than 1, then minus 1/2. Minus 1/2 is somewhere here, I guess. Well, if this is 0 minus 1, so minus 1/2 is something like here. Now, don't forget that I am supposed to be in this area. So it's not just any x which is less than 1/2, but only those x less than minus 1/2 which belong to this area, which means only these guys. Now, in the first one, we got this area completely, everything which is less than minus 2. In the second case, we are considering this area, but only those x's which are less than minus 1/2 fit the bill. These are not a solution to our equation. And so let me put it here. Minus 2 less than x less than minus 1/2. That would be a true solution, x less than minus 1/2, but it's still supposed to be greater. So this should be really a true solution to this. So the first area gives me less than minus 2, and the second area gives me starting from minus 2, including, by the way, so there is no gaps here, the point minus 2 is included, up to minus 1/2. Now, the third area, C, is this one. So x is greater or equal to, well, let's put it this way. 1 less than x. So I prefer to have always less signs. All right. What's here? Well, we are to the right of this point where this is equal to 0, and obviously to the right of this point, which means everything, all absolute values, should be just dropped. So it would be x plus 2 minus x minus 1 less than 0, which means x plus 2 minus x plus 1 less than 0, x goes out, 3 less than 0, which is not right, which means none of the values in the C area would be a solution. So there are no more solutions. We found all solutions in the A area, all solutions to the B area, and basically no solutions in the C. So only the numbers from minus 1/2 to the left are actually solutions to our equation. So we can combine this and this because they are basically glued together, these two areas, and we can conclude that the whole solution to this particular inequality is x less than minus 1/2. This is a total solution, which basically we have found out by combining these two. Everything to the left of minus 1/2. And, well, obviously, if x is equal to minus 1/2, I guess we have to expect it to be equal to 0, right? Let's check it out just in case. So this would be what? 1.5, right? 2 minus 1/2, it's 1.5. This is minus 1/2 minus 1, it's minus 1.5, but absolute value gives me 1.5. So it's 1.5 minus 1.5 equal to 0, which is exactly what we were looking for. So if at the point x equals to minus 1/2, this is 0, and everything to the left of it would be less than 0. And incidentally, everything to the right will be greater than 0. Now, just as an illustration, let's do it graphically, just to confirm that we are right. So first we have to build the graphs of this and then subtract one from another, right? All right, so this would be y equals absolute value of x. Why? Because for positive x, it's supposed to be the same as y equals x. For negative x, it would be the same as y equals minus x. So I just combine these two pieces of two graphs, and that's my graph y equals absolute value of x. Now, plus 2, it means I have to shift the graph to the left by 2 units, right? This is 1, this is 2, this is minus 1, this is minus 2. So my graph of this particular element, absolute value of x plus 2, should look like this. This is original, which is just used to shift it. So this is y equals absolute value of x plus 2. Now, x minus 1 means the graph should be shifted to the right by 1. And the graph would be this, obviously. This is y equals absolute value of this. Now, we don't need our original absolute value of x. We used it completely to shift it left and right. Now we have these two graphs. And we have to subtract one from another. From this graph, we have to subtract this. Again, the best thing is to use the key points, exactly where the graph changes the behavior from decreasing to increasing. Because in between these points, graph behaves as a linear function, right? Because I can always say that above 1, it's x plus 2 minus x minus 1. So I can drop the absolute value. And in between, from minus 2 to 1, I can drop this one, absolute value, just leave it as it is, and change the sign of this. But it's still a linear function. So everywhere it's linear functions. So let's find what exactly the key points, and then we will think about it. What will be in case x is equal to 1? Well, this is 0, and this is 3, right? So if I subtract, this would be, I'll use the red. This would be my point of the new graph, which is a difference between these two. And that would be 3. Now, minus 2. Minus 2, this is equal to 0. Minus 2, minus 1, it's 3, absolute value, 3 minus, it will be minus 3. Okay, so the graph would be here at minus 3. Okay. So we have 2 points here and here. Now, in between these points and outside of these points, the graph is a linear function. So I can just do it exactly. By the way, at 0, it's equal to 2 minus 1, 1, right? So it would be here. So the graph would go like this. It's a linear function. And it's very easy to see right now that we have crossed the x-axis in between 0 and minus 1. So that's where minus 1/2 actually is. What would be outside of this? Well, think about it this way. As I'm moving to the right, I'm adding something to this graph, and I'm adding exactly the same thing to this graph, which means the difference between them, which is minus sign, should not change. So whatever the value was here, which is 3, should be retained, and the graph should go constant. And if you remember, the area C was like 3 supposed to be less than 0 and no solutions, etc. But 3, it was on the left side because it's a constant. Now, same thing here. If I move to the left, one graph is increasing and another graph is also increasing, but exactly by the same value, which means the difference between them should remain the same, whatever it was before, which is -3. Which means it should be constant -3. And again, in area A, if you remember, we had the this particular expression as equal to -3. -3 less than 0, always, which means all the x's on the left correspond to our equation. So this is a confirmation, a graphical confirmation, that starting from this point and to the left, which is -1/2, exactly what we have basically derived, the graph is negative, and that's exactly what we wanted to get. So this lecture was about how to approach inequalities which contain absolute value. Remember, if you have an absolute value of some expression, in this case it's a linear expression, you always have to find the key point where it's equal to 0. And then, if you have many expressions, like in this case I have 2, then mark all these critical points where each particular absolute value is equal to 0, and consider your inequality on each interval. These points are dividing all the real numbers. Well, that's it for this lecture. Thank you very much. And probably I will include certain number of interesting problems in the next lectures about inequalities. Thank you.